All right, let's take a look at Chapter 2, Describing Distributions with Numbers. In Chapter 2, we cover measuring center, the mean, measuring center, the median, comparing the mean and the median, measuring spread, the quartiles, the 5-number summary and box plots, spotting suspected outliers, measuring spread, the standard deviation, choosing measures of center and spread using technology, organizing a statistical problem. Measuring center, the mean. The most common measure of center is the arithmetic average or mean. To find mean, x bar, pronounce x bar, of a set of observations and their values and divided by the number of observations. To find the mean, add their values and divide by the number of observations. If the in observations are x1, x sub 2, x sub 3, so on and so forth until x sub n, then their mean is the sum of all of those values, x1 plus x sub 2 plus so on and so on until you reach the last value of x sub n divided by n, or more compactly written as x bar equals 1 divided by n times the sum of all the x values. Measuring center, the median. Because the mean cannot resist the influences of extreme observations, it is not a resistant measure of center. Another common measure of center is the median. The median M is the midpoint of a distribution, the number such that half of the observations are smaller and the other half are larger. To find the median of a distribution, arrange all observations from smallest to largest. If the number of observations n is odd, the median m is the center observation in the ordered list. If the number of observations n is even, the median m is the average of the two center observations in the ordered list. You can always locate the median in the ordered list of observations by counting up n plus 1 and divide by 2 from the start of the list. Measuring center. Use the data below to calculate the mean and median of the commuting times in minutes of 15 randomly selected North Carolina workers. And here we have a chart of their responses. If we sum all of the values in the chart and then divide by the 15 randomly selected workers, then we find that we have an arithmetic average, x bar, of 22.5 minutes. Here in the last slide, let me go back. In the last slide, there at the bottom, they have given us a stem and leaf plot. So if you remember these from the previous chapter, they've rearranged all the data. So you see we have a 5 on the list, and then we have a 10, a 10, a 10, a 10, a 12, a 15, a 20, a 20, a 25, a 30, a 30, a 40, a 40, nothing in the 50s, and then a 60. So they've taken the numbers in the chart and they've just ordered them through this stem and leaf plot here. so. The median in your sorted list is 20. So first we find the mean, and then we found the median. Comparing the mean and median. The mean and median measure center in different ways, and both are useful. The mean and median of a roughly symmetric distribution are close together. If the distribution is exactly symmetric, the mean and median are exactly the same. In a skewed distribution, the mean is usually farther out in the long tail than is the median. Measuring spread, quartiles. A measure of center alone can be misleading. A useful numerical description of a distribution requires both a measure of center and a measure of spread. We could look at the largest and smallest values, and we will, but like mean, they are obviously affected by extreme values, so we will examine other percentiles. To calculate quartiles, arrange the observations in increasing order and locate the median M. The first quartile, Q1, is the median of the observations located to the left of the median in the ordered list. The third quartile, Q3, is the median of the observations located to the right of the median in the ordered list. 5-number summary. The minimum and maximum values alone tell us little about the distribution as a whole. Likewise, the median and quartiles tell us little about the tails of the distribution. To get a quick summary of both the center and spread, combine all 5 numbers. The 5-number summary of a distribution consists of the smallest observation, the first quartile, the median, the third quartile, and the largest observation, written in order from smallest to largest. Min, Q1, M for median, Q3, and max. Box plots. The 5-number summary divides the distribution roughly into quarters. This leads to a new way to display quantitative data, the box plot. How to make a box plot. A center box spans the quartiles Q1 and Q3. A line in the box marks the median M. Lines extend from the box out to the smallest and largest observations. 5-number summaries and box plots. Consider a second travel times data set, these from New York. Find the 5-number summary and construct a box plot. First, we want to sort the list. So step 1 is sort the list. And then we locate the middle of the list to find the median. And then we find the middle of the lower list to find Q1 and the middle of the upper list to find Q3. The median is the halfway point between 20 and 25. Q1 is the halfway point between 15 and 15. Q3 is the halfway point between 40 and 45. The min is 5 and the max is 85. Generally, we write them in order from min to max. To plot, we have a scale, like a ruler, x-axis, and then we plot the box, which spans from Q1 to Q3, the middle 50% of the data, with a line in the middle for the median. And then a long horizontal line which stretches from the min to the max, going through the box. Spotting suspected outliers. Having observed that the extremes, minimum and maximum, don't describe the spread of the majority of the data, we turn to the difference of the quartiles. The interquartile range, or IQR, is the difference between Q3 and Q1. In addition to serving as a measure of spread, the interquartile range, IQR, is used as a part of a rule of thumb for identifying outliers. Take 1.5 times the distance of the interquartile range is the rule for our outliers. Call an observation a suspected outlier if it falls more than 1.5 times the interquartile range above the third quartile or below the first quartile. Spotting suspected outliers in this example. In the New York travel times data, Q1 was 15 minutes and Q3 was 42.5 minutes. So the IQR equals 42.5 minus 15, which is 27.5 minutes. For these data, 1.5 times IQR is 1.5 times 27.5, which is 41.25. Q1 minus 41.25 is negative 26.25. And Q3 plus 1.5 times the IQR is 83.75. Any travel time shorter than negative 26.25 minutes or longer than 83.75 minutes is considered an outlier. So the maximum observation, 85 minutes, would be a suspected outlier. Measuring spread, standard deviation. The most common measure of spread looks at how far each observation is from the mean. The measure is called the standard deviation. The variance, S squared, is a set of observations. The variance of a set of observations is an average of the squares of the deviations of the observations from their mean. In symbols, the variance of the n observations, x sub 1, x sub 2, x sub 3, on and on till x sub n, is S squared equals the quantity x1 minus the mean squared plus the quantity x2 minus the mean squared, so on and so forth, until you finally sum the final quantity of xn minus the mean squared, and you divide that by n minus 1. Again, more briefly, S squared, or the variance, is 1 divided by n minus 1 times the sum of the differences squared. The standard deviation S is the square root of the variance. S is the square root of the variance, so S equals the square root of S squared. Calculating the standard deviation. In this example, consider the following data on the SAT critical reading scores for 5 Georgia Southern University freshmen in 2010. First, calculate the mean. Second, calculate each deviation. Deviation is an observation minus the mean. The mean is to sum these 5 values that we see in the blue dots and divide by 5, which gives us the result of 548. Then 650 minus 48, so 650 minus the mean. We're looking at that farthest dot to the right, and what we're saying is the deviation between the mean and the farthest observation is 102. And what we do is calculate each deviation and square those. So square each deviation, then find the average squared deviation, calculate the sum of the squared deviations, divide by n minus 1. This is called the variance. Calculate the square root of the variance. This is the standard deviation. Generally, we do this in the form of a chart when we're in class together. So we have a column for the observation, the x. We'd have a column for the deviation, so x minus the mean, and then we would have a column for the deviation squared, so that we would just take the deviation and square it, and finally sum that final column and divide by n minus 1, here 4, and then take the square root. Average square deviation is the sum of that final column divided by 4, which is 6,220. This is the variance. Standard deviation equals the square root of the variance. So the square root of 6,220 is 78.87. Properties of S. N minus 1 is called the degrees of freedom. S measures variability about the mean and should be used only when the mean is chosen as the measure of center. S is always 0 or greater than 0. S equals 0 only when there is no variability. This happens only when all observations have the same value. Otherwise, X is greater than 0. As the observations become more variable about their mean, S gets larger. S has the same units of measurement as the original observations. For example, if you measure weight in kilograms, both the mean X bar and the standard deviation S are also in kilograms. This is one reason to prefer S to the variance S squared, which would be in kilograms squared. Like the mean X bar, S is not resistant. A few outliers can make S very large. Choosing measures of center and spread. We now have a choice between two descriptions for center and spread, mean and standard deviation, or median and inner quartile range. Choosing a summary. The 5-number summary is usually better than the mean and standard deviation for describing a skewed distribution or a distribution with strong outliers. Use X bar and S only for reasonably symmetric distributions that are free of outliers. Organizing a statistical problem. As you learn more about statistics, you will be asked to solve more complex problems. Here is a 4-step process you can follow. Organizing a statistical problem, a 4-step process. State. What is the practical question in the context of the real-world setting? Plan. What specific statistical operations does the problem call for? Solve. Make graphs and carry out calculations needed for the problem. Conclude. Give your practical conclusion in the setting of the real-world problem.